Let's look at section 9.4. Let's review some formulas. The first one is multiplying radicals. The nth root of A times the nth root of B is equal to the nth root of AB, which means if I'm multiplying two different radicals, I could combine it into one larger radical. Very similar is when we're dividing radicals. If we have the nth root of A divided by the nth root of B, this is equivalent to the nth root of A over B. And so let's try some problems. For question 1, we have the square root of 12 times the square root of 75. We can use the multiplying property of radicals. So this is the same as the square root of 12 times 75. And if we multiply 12 times 75, you will get that this is equivalent to the square root of 900. And using a calculator, we can simplify the square root of 900 as 30. Let's look at our second example. We have 7 times the square root of 32 times 5 times the square root of 6. To do this, we'll multiply the 7 times the 5, and that's going to give me a 35. And the square root of 32 times the square root of 6 is the same as the square root of 32 times 6. Now we can simplify this further. This is equal to 35 times the square root of 192. Now, if you take the square root of 192, it does not come out nicely. So we have to use the factor tree for 192. Well, we know 192 is 32 times 6. And we could break down 6 as 2 times 3. I know 32 is 2 times 16. 16 is 2 times 8. And 8 is 2 times 4. And 4 is 2 times 2. So we could rewrite this as 35 times the square root of, let's see how many 2's we have. We have 1, 2, 3, 4, 5, 6 2's. 1, 2, 3, 4, 5, 6 2's, and 1 3. Now, since we're looking for the square root, we need to look at the pairs. We have a pair here. We have a pair of 2's here. Another pair of 2's here. And so there's 3 pairs of 2's. That means I need to multiply that 35 with a 2 times a 2 times a 2. There's 3 pairs of 2's. And what's left inside is the square root of 3. If we multiply 35 times 2 times 2 times 2, we get this is equivalent to 280. 280, and we have the square root of 3. So sometimes it's better not to multiply 32 times 6 out and just rewrite 32 times 6 as the prime factorization. 2 times 2 times 2, 6 times, and then a 3. So in some cases, it's not wise to multiply 32 times 6. It's better just to probably find the prime factorization here. Let's look at example 3. We're going to multiply this out. So let's multiply the radicands together. We have 6 times 10 on the inside. So let's write that as a 60. A to the 7th times A to the 5th. That's A to the 12th. You have to add the exponents when you're multiplying them together. B to the 6th plus B to the 9th. We're going to add the exponents. That's B to the 15th. Let's look for the prime factorization of 60, and you can do that on your own. The prime factorization of 60 is 2 times 2 times 3 times 5. That's the prime factorization of 60. And we'll copy a to the 12th and b to the 15th. Now we're looking for groups of 2. So we have one pair of 2's here. So that's going to go in the front. So this is equivalent to 2 in the front. We have a 3 and a 5. So that's going to stay on the inside since there's no pairs. So let's write a 15 on the inside. And for the a to the 12th, we're going to divide the 12 by 2. And that gives us 6 with a remainder of 0. That means we have an a to the 6th on the outside with no a's on the inside. We'll take the 15 and divide that by 2. We get 7, remainder 1. So that means we have a b to the 7th on the outside and a b to the 1st on the inside. So that's our answer. 2a to the 6th, b to the 7th, times the square root of 15b. Let's look at question 4. This is the cube root, so we're not looking for pairs anymore. We're looking for groups of 3. So let's rewrite this. This is the cube root of, well, let's multiply the x's with the x's. X to the 10th times x to the 6th is x to the 16th. Y to the 14th times y to the 19th. We add those together. We have z to the 17th times z to the 8th. That gives us 25. So this is z to the 25th. Since we're looking for groups of 3, we'll take the exponents and we'll divide each of these exponents, the 16, the 33, and the 25 by 3. We're looking for groups of 3. 16 divided by 3 is 5 with a remainder of 1. 33 divided by 3 is 11 with a remainder of 0. 25 divided by 3 is 8 with a remainder of 1. So let's write our answer out. This is going to be the exponents on the outside. So let's write it as x to the 5th, y to the 11th, z to the 8th, times the cube root of, now these are the exponents on the inside. So we have an x to the 1st, or just x. There's no y's, and a z to the 1st. So this is our solution, x to the 5th, y to the 11th, z to the 8th, times the cube root of xz. Let's look at some special cases of multiplying a square root with the same square root. Let's consider the square root of 3 times the square root of 3. This is equivalent to the square root of 3 times 3, or the square root of 9, and that's equal to 3. So hopefully you can see a pattern. If I do the square root of 4 times the square root of 4, this is equal to the square root of 4 times 4, which is 16, and that's 4. Now let's do it one more time. The square root of 5 times the square root of 5 is equal to the square root of 25, which is exactly 5. So there is a pattern. If we take the square root of any number x times the square root of any number x, we just get x. So the square root just disappears, and all we're left with is the radicand. So let's look at example 5. We'll distribute the square root of 5 times 10. So this is the square root of 5 times the square root of 10. And then we'll distribute the square root of 5 times the square root of 5. So this is negative square root 5 times square root of 5. Now, what's the square root of 5 times the square root of 10? That's the square root of 5 times 10. And we just realized that the square root of 5 times the square root of 5 is 5. The roots just disappear if it's the same index. We can simplify this further as the square root of 50 minus 5. But we could break down the square root of 50 with the prime factorization. This is the square root of 2 times 5 times 5. And since we're looking for groups of 2, we'll take that pair out to the front. And this simplifies our solution as 5 root 2 minus 5. Let's look at the example 6. We have the square root of 15 times the square root of 30. We're just going to rewrite that inside one radical, 15 times 30. We'll distribute the root 15 times root 35 now, so that's the square root of 15 times 35. Now, a lot of people might feel tempted to multiply these numbers out, but I'm just going to start by doing the prime factorization of 15 and 30. It just makes it easier for me not to multiply it out. So let's find the prime factorization of 15. Well, 15 is 3 times 5. 30 is 2 times 3 times 5. Same thing here on the right. I'm not going to multiply 15 and 35. It's better just to find the prime factorization. And 35, that's going to be 5 times 7. Now we're looking for pairs. I have a pair of 3s and a pair of 5s. So that's going to go in the front. So this is equal to 3 times 5 in the front, leaving us with a single 2 on the inside of the radical. So this is a 2 on the inside, minus now we have a pair of 5s. So that goes out to the front. And on the inside, we're left with a 3 times a 7. Let's simplify the 3 times 5. That's 15. This is 15 root 2. And we can simplify the right side. This is going to simplify to 5 times the square root of 21. For question 7, this one is a little bit more complicated, but we'll just do it slowly. We'll take our time. So let's distribute the 6 square root of 3 to 9 root 6. So that's 6 times 9. We're multiplying the 6 and the 9 together. And then we'll multiply the root 3 with the root 6. That's root 3 times 6. Minus, we have a 6 times a 4. So that's 6 times 4 in the front. And the square root of, we're multiplying that 3 now with the 15. So this is 3 times 15 on the inside. Let's simplify this a little bit further. 6 times 9 is 54. And we'll do the prime factorization of the inside here. This breaks down into 2 times 3 for the 6. And then we'll be able to factor that soon. We will be able to take that square root soon. 6 times 4, that's 24. And we could do the prime factorization of 3 times 15. This is 3 times 3 times 5. Now I'm looking for groups of 2. So let's circle these pairs. So this is going to be 54 times 3 in the front and a square root of 2 on the inside. This is 24 times a 3 in the front with a square root of 5 on the inside. 54 times 3 is 162, so this is equal to 162 root 2. And 24 times 3. That's equal to 72. So this is 72 times the square root of 5. And that's it. We cannot add or subtract these because they have different radicals. So this is our final answer. 162 root 2 minus 72 root 5. In example 8, we'll use distribution again. Let's distribute the square root of m to the 5th times n to the 9th to both of these terms. And don't forget, we need to add the exponents if we're going to multiply them. M to the 5th times m cubed is going to give us m to the 8th. In example 8, we'll use distribution to multiply m to the 5th times n to the 8th into each of these radicands. So this is equal to the square root. We have m to the 5th times m to the 3rd. That's going to give us m to the 8th. N to the 9th times n to the 4th. That's going to give us n to the 13th. Now we'll do it again. We'll have a new radical now. M to the 5th times m to the 8th. That's m to the 13th. So that's m to the 13th. Again, it'll be inside one big radical. And n to the 9th times n to the 7th. That's going to be 9 plus 7, which gives us n to the 16th. Now remember, we're looking for groups of 2, so we'll take each of these exponents and divide them by 2. We'll divide each of these exponents by 2. 8 divided by 2 is 4, remainder 0. And 13 divided by 2, that's going to be 6, remainder 1. And 16 divided by 2, that's 8, remainder 0. Now notice I only did 13 divided by 2 once because I know if I do it once for the m to the 13th, that's the same for the n to the 13th. So let's look at the first radical here. We know that 8 divided by 2 is 4, remainder 0, so that's m to the 4th on the outside, and no m's on the inside. 13 divided by 2, that's n to the 6th, with a remainder of 1 inside, so that's n on the inside. 13 divided by 2 is 6, so that's going to give me an m to the 6th on the front, with a remainder of 1 m on the inside, because the exponent is 1. 1 because if you divide the 13 by 2, you get a remainder of 1. 16 divided by 2 gives us 8, so that's n to the 8th in the front with a remainder of 0, so there's no n on the inside. Example 9, you can pause this video and try this one on your own. Alright, let's try it together. We have the cube root of a to the 7th times the cube root of a to the 11th. Again, you're going to have to add these exponents together. So 7 plus 11 gives me a to the 18th. We have b to the 10th times b to the 35th. We're going to add that together. That's b to the 45th. And since there's no c's inside this radicand, we're just going to put that c to the 13 on the inside. Plus, again, we have the cube root. We'll multiply that a to the 23rd with the a to the 7th, so we'll add the exponents. This is a to the 30th. We have a b to the 10th, and well, there's no b's here, so we're just going to put b to the 10th. C to the 13th times c to the 8th. We'll just add those exponents together. That's going to be c to the 21st. And now we can simplify this by, again, looking at the exponents and dividing each of our exponents by 3 because that's the index. So we'll take each of these exponents and divide them by 3. We'll take the 18 divided by 3, the 45 divided by 3, the 13 divided by 3, the 30 divided by 3, the 10 divided by 3, and the 21 divided by 3. 18 divided by 3, that's 6 with a remainder of 0. 45 divided by 3, that's 15 with a remainder of 0. 13 divided by 3, that's 4 with a remainder of 1. 30 divided by 3, that's 10 with a remainder of 0. And 10 divided by 3, that's 3 with a remainder of 1. And 21 divided by 3, that's 7 with a remainder of 0. Now we can finally finish the problem. Now the number in the front here is going to tell us the exponents in the front, and the number in the back is going to tell us the exponents on the inside. We have an a to the 6th, a b to the 15th, and a c to the 4th. And that's from this 6, this 15, and this 4. Times the cube root of, we have no a's, no b's, but one c on the inside. So this is the cube root of c. Plus, we have an a to the 10th, a b cubed, a c to the 7th, and that's from this 10, this 3, and this 7, with a cube root of, we don't have any a's on the inside. We do have one b, so that's b to the first, or just b, and there is no c's. So that's it. This is our simplified problem. For example 10, we have to remember how to FOIL out problems. The F stands for the first with the first, so we'll multiply the square root of 3 times the square root of 6. Then the O stands for the outside, so we'll multiply the square root of 3 with the square root of 2. The I stands for the inside, so that's the square root of 8 times the square root of 6. And the L stands for the last part, so the square root of 8 times the square root of 2. So let's simplify this. The square root of 3 times the square root of 6 is first with the first, so that's the square root of 18. We'll multiply the square root of 3 times the square root of 6, that's the square root of 6. Don't forget that negative. Sometimes students forget that, so be careful. The square root of 8 times the square root of 6 is next, so that's going to give us the square root of 48. And then we have the square root of 8 times the square root of 2, that's the square root of 16. Again, be careful with that negative. There's a negative here because we multiplied with a negative square root of 2. So let's simplify. I can simplify the square root of 18 a little bit further. We can make a factor tree, and this is 2 times 3 times 3. The square root of 6 is just 2 times 3, so there's no pairs. I'll leave it as the square root of 6. The square root of 48, I can simplify that as 2 times 2 times 2 times 2 times 3. That's the prime factorization of 48. And the square root of 16, that's a easy square root to do. That's just 4. We can do that on our calculators. Notice I'm looking for pairs. I have a pair of 2's here and a pair of 3's. So this simplifies to 3 root 2. We have a negative square root of 6. We have 2 times 2 in the front, which makes 4. So this is a 4 root 3. And we have a negative 4. Now look carefully. Can we add anything together? We have a square root of 2. There's no other square root of 2's. We have a square root of 6. There's no other root 6's. We have a root 3. There's no other root 3's. So that's it. We can't simplify this any further. That's it for example 10. For example 11, we'll FOIL it out again. We'll multiply 2 root 3 times 8 root 7. 2 times 8, that's 16. We have 16 root, and then on the inside is 2 times 7, which gives me 14. Then we'll multiply 2 root 2 times negative 5 root 2. That's going to give us negative 10, because 2 times 5 is 10. And root 2 times root 2, that's going to be the square root of 4. Now we'll multiply negative 9 times 8, that's negative 72. And we have root 7 times root 7, which is root 49. We can multiply now 9 times 5, or actually negative 9 times negative 5, that's a plus 45. And we have a root 7 times a root 2, which gives us root 14. Now let's simplify this further. I cannot simplify root 14 because the prime factorization is 2 and 7. There's no pairs in there. So we'll leave it as the square root of 14. We have 10 times the square root of 4. That's the same as 10 times 2. So notice here how we got the square root of 4. We multiplied the square root of 2 times the square root of 2. So we can easily have changed that to a simple 2 instead of writing it as the square root of 4. So if you're multiplying the same square root with the same square root, it's often best just to write it as being multiplied by 2. We have minus 72, and the square root of 49, that's 7. Again, how did we get that square root of 49? We multiplied the square root of 7 times the square root of 7, which simplifies to 7. So we could skip this step of writing root 49 and just write it as a multiplying by 7. And we'll simplify the right side here, which is just root 14. We can't do anything with that. Now let's collect like terms. We have 16 root 14 plus 45 root 14. That gives us 61. So this is 61 root 14. Negative 10 times 2, that's negative 20. And negative 72 times 7 is 504. So this is negative 504. Let's simplify it a little bit further. We have, this is 61 root 14. And negative 20 minus 504, that's negative 524. Question 12, we have 6 plus 7 square root of 3 squared. What does this square term mean? Well, it means I need to multiply 6 plus 7 root 3 to itself twice. So let's do that. We'll multiply 6 plus 7 root 3 to itself twice. Now that means we have to FOIL. So let's FOIL. 6 times 6, that's 36. 6 times 7 is going to be 42. This is 42, but we have to add that root 3 with it. We have 7 times 6, again that's a 42. And we'll also have to add that root 3 with it. So this is 42 root 3. And then we'll multiply 7 times 7, that gives us a 49 in the front of this radical. And the square root of 3 times the square root of 3, that's multiplying by 3. Again, when you multiply the square root of 3 times the square root of 3, that's the same as multiplying by 3. Now let's simplify. Let's collect like terms. We have 42 root 3 plus 42 root 3. That's 84 root 3. I'll bring down that plus 36. And then we'll simplify 49 times 3. 49 times 3 is 147. And then we could add 36 plus 147. This gives me 183 plus 84 root 36. Now, it doesn't matter if you have the 183 on the other side, on the right side, or if you have the 84 root 36 on the left. It doesn't matter. It's still the same solution. What are conjugates? Well, conjugates are of the form a plus b and a minus b. Now, why do we care about conjugates? Well, the nice thing is, if we multiply two conjugates together, you actually get something very simple. You get a squared minus b squared. We could FOIL this out if we wanted to, but just be aware that you're going to get the same solution as just doing a squared minus b squared.
Notice, in this problem we have the square root of 26 plus the square root of 3 times the square root of 26 minus the square root of 3. These are conjugates. They look exactly the same, but the only difference is we have a plus sign here and a minus sign here. So they are conjugates, which means we can use the shortcut. The shortcut is multiply the first with the first and the last with the last. This only works if they're conjugates. We can multiply the square root of 26 times the square root of 26. And then we'll multiply square root of 3 times negative square root of 3. So we have negative square root of 3 times square root of 3. The square root of 26 times the square root of 26, that simplifies. That's equivalent to 26. The square root of 3 times the square root of 3, that's exactly 3. This simplifies to 26 minus 3, or 23. So it's very important that we remember the shortcut. If we multiply the same square root by the same square root, we just get the radicand back. And so this simplifies fairly quickly when we use the shortcut. But if you want to FOIL, you will still get the same answer. If you're going to FOIL this out, you will still get the same answer, but you're just wasting your time. So learn the shortcut.
This shortcut only works if they're conjugates, so double check that they're conjugates. And in this case we do. We have 9 root 6 plus 3 root 8. And the same thing, except this is a minus. So these are conjugates, which means all I have to do is multiply the first with the first and the last with the last, and I'm done. So let's multiply 9 root 6 times 9 root 6 minus 3 root 8 times 3 root 8. Now 9 times 9, that's 81. I know the square root of 6 times the square root of 6 is 6. And for this side, we have 3 times 3, that's 9. And the square root of 8 times the square root of 8 is 8. We can simplify now. 81 times 6, that's 486. And 9 times 8, that's 72. And so if we subtract these two, we get 414.